Yep, go ahead. Number 21.
Actually, 36, sorry. And 41.
Chapter 20, problem 36.
Specifically C.
The one that says give the products of reaction of methylpentanoate with each of the following reagents.
Yes.
That's the problem we're talking about. So that's methylpentanoate. So the first reaction is a saponification. Hydroxide and heat. And then this aqueous acid workup that make the carboxylic acid. B is a transesterification. So you're treating it with a different alcohol. And you're adding a lot of that. So you're going to replace the OCH3 with this alcohol. C, that's the one you were concerned with, right? Treating that with diethylamine and heat. They've left the acid catalyst out here, but this is a secondary amine reacting with an ester. Actually,
Sorry, you're cutting out a lot. I didn't hear that.
Actually, I guess you don't need an acid catalyst for this. You can just do this without the acid catalyst. But you're reacting an ester with an amine, so you're going to make the amide and the alcohol. So you're going from a more reactive carboxylic acid derivative, the ester, to a less reactive carboxylic acid, the amide.
So then, my question would be for these esters, will it mostly be an addition and an elimination, like the substitution?
Generally, for all the acid derivatives, they're mostly going to be nucleophilic acyl substitutions or acyl addition elimination mechanisms. This one's acid catalysis, right? So this one's the 6-step mechanism, basically just like the Fischer esterification, except the leader group is methanol instead of water. These two, both of these are 3-step mechanisms. Attack with hydroxide, kick out methoxide, and then proton transfer, and then the acid workup converts the carboxylate salt to the carboxylic acid. This one's attack with the nitrogen, right? Loss of the methoxide, and then the methoxide plucks off the hydrogen from the intermediate to make the neutral stuff. So yeah, that's an addition elimination. D is a little bit more going on. Because in D, you're first doing nucleophilic acyl substitution. To make the ketone, but then the ketone doesn't stop reacting, so you do a nucleophilic acyl addition. So that's two successive reactions, one of which is nucleophilic acyl substitution, but then the other isn't. The other is a nucleophilic acyl addition, just like we did back in chapter 17 in last semester. E is a reduction. used here? Ether? Yep. We use ether again, and that could take it to the primary alcohol. So that again is a nucleophilic acyl substitution to make the aldehyde. And then the aldehyde reacts further with additional lithium aluminum hydride to go the rest of the way. And then F is dival. At low temperature. And then you work that out with aqueous acid P. And that makes the aldehyde and stays there. The intermediate after the dival step is actually that, which looks like a hemiacetal. And then the hemiacetal is cleaved to the aqueous acid and heat to generate the aldehyde. So dival doesn't actually reduce it all the way to the aldehyde. Dival converts it to the hemiacetal, and then hydrolysis. And I don't know if you were here before, we were talking about all the dival reductions generate an intermediate that is hydrolyzed to the aldehyde, not the aldehyde directly. That's all of them, right? The first three were straightforward, right? The first three were just nucleophilic acyl substitution mechanisms. D and E were nucleophilic acyl substitution followed by nucleophilic acyl addition, and then F is a little weird, right? F is actually a nucleophilic acyl addition reaction across the carbonyl group. Sorry, wait, that's an OCH3, not an OH. So you're doing a nucleophilic acyl addition reaction of the dival across the carbonyl group, the aluminum at the oxygen, the hydrogen at the carbon, and then you're hydrolyzing that to generate the aldehyde. So that one is not a nucleophilic acyl substitution. Does that answer all of your questions? I did actually record this one. I was planning to record all of it, but then Isabel told me she couldn't hear me, so I messed with the mic and then forgot to hit record again. Oh well. Fortunately, the answer key is postable, and pretty much everything we did up until now was off the practice exam. I don't think I ever actually talked about transesterification directly in class, but the mechanism is pretty much the same, except instead of water, you've got another alcohol. Transesterification is pretty common when you make lactose too. We'll take a acyclic ester that has a hydroxyl group somewhere else in the molecule and treat it with aqueous acid and it cyclizes. I guess I could actually have taken my mask off since there's no one else in the lecture hall. Maybe that's why I was muffled before.
Is there any chance we can go over the roadmap?
Yeah, we can go over all of the problems, anything you want. Which one's that? Page 5?
Page 6.
Page 6. Oh, that one. Yep. Okay. That's problem 1753. so compound D, C8H14O, that reacts with a phosphorus. This is the phosphorane. You can also write that in Ylid form. So that's a Wittig reaction. Into compound E, C9H16. So you're adding the CH2 and you're getting rid of the oxygen, which means this is going to have a ketone in it, or an aldehyde. And we're just converting that ketone or aldehyde into amine. We're going to treat this with lithium aluminum hydride. Form C8H16O. They're isomers in unequal yield. Oh, sorry, wait, wrong. This compound D is treated for method D. Those are alcohols. Probably that means this is cyclic. And you're going to get a cis and trans isomer here, much like we did in the lab, where we have to bring in reagents to both sides. Likely. And then we're treating F and G, which are C8H16O. Concentrated sulfuric acid. Produce H. C8H14. Probably that's dehydration of the alcohol. And the cis and the trans alcohol will both dehydrate to the same thing, just like they did in the lab, right? Where we had the cis and trans 2-methyl-1-phenylcyclohexanol, and that dehydrated to the mixture of the two alkenes. In this case, we just get one alkene. And then ozonolysis of that followed by zinc and acetic acid. So that's mild reduction. Yields a ketoaldehyde. And they don't give us the structure of that. They don't give us the formula. But. And then oxidation of this, we make with chromium 6. So maybe potassium bichromate. Sulfuric acid produces that compound. Identify compound D through H, pay particular attention to the stereochemistry of D, explain whatever. All right, so that's what we're looking at. So probably easiest to work backwards in this case. We know this is a ketoaldehyde, and we know that aqueous chromium 6 will convert aldehydes to carboxylic acids. So the ketoaldehyde is probably just this. Where we've got an aldehyde instead of the carboxylic acid, and then that gets oxidized to the carboxylic acid, and then won't affect the ketone because the ketone is already as oxidized as it can be. So then if we work backwards to the alkene, what we're going to do is just close this up. Right, so that's a 7-membered ring with a double bond in it.
Wait, shouldn't the ring be 6-membered?
That product has, oh, sorry, yeah, the ring is 6-membered ring, yeah, because it's between 2 and 7. Yeah. So carbon 2 has a methyl group off it, and carbon 6 has a methyl group off it. Just one alkene. So that dehydration product probably came from this. But there were 2 possible versions of F and G, both of which dehydrate to the same thing. So you could be looking at that, right? Or you could be looking at this. Actually, I guess I should draw the, I should leave the methyl groups alone and change the stereochemistry of the alcohol. So when I say pay particular attention to the stereochemistry of D, right, D is going to be the corresponding carbonyl, and D might be that, but D might also be that. So are the 2 methyl groups cis to each other, or are they trans to each other?
I'm confused how you labeled the F and G things.
So I know that this was a dehydration product.
I understand what you did, but why did you label, like,
Oh,
I don't know, wouldn't you want,
because I know that C8H16, no, there were 2 isomers of this. And both of those 2 isomers, when treated with sulfuric acid, generate the same alkene.
yeah, I understand. I'm just saying, like, why do you have the one where the,
Oh, that's random. Why is one F and the other one G? Doesn't matter.
because, like, those 2 sets, like, wouldn't one of those sets be F and the other one be G? Because of, like, the opposite side?
No, because this combination of F and G would have come from this ketone by lithium hydride attacking either the top or the bottom. And this combination of F and G would have come from this ketone. Only one of those combinations of F and G is correct, the other one is incorrect.
Oh, never mind. Okay, thank you.
And if you look at it, you'll notice that F is G here. If you rotate around this bond, around this axis, the OH and this one go up, this one goes back, so these are identical. So you wouldn't actually get 2 different products from reducing this one. You'd only get 2 different products from reducing that one. So D has this stereochemistry, not this stereochemistry. Does that make sense? Right? Because attacking from the top face here pushes it back on the same side as that, but attacking from the bottom face here pushes it up on the same side as that. Those are the same molecule, just rotated 180 degrees. Right? So it can't be this, the fact that we get two different products means that the two methyl groups have to be on the same side of the ring in compound D. And then compound D, going to the Binning reaction, becomes that C9H16. The unsaturation number there is 2, one ring, and then the new pi bond that you've just put in. So that's the tricky part of this question. The tricky part of this question is recognizing whether the two methyl groups are on the same side or different side in compound D.
Question: Can we draw that like with the two like carbons coming forward instead of back? That's the same thing, right?
Yeah.
As long as they're going like the same way.
So this, if I rotate it 180 degrees,
Yeah, like that's all that I just.
it becomes that. And if I rotate this one 180 degrees, it becomes.
Okay, cool. Thank you.
So it's giving you a mixture of cis and trans, where the alcohol is on the same side as the two methyl groups are on the opposite side of the two methyl groups. But it's crucial that the two methyl groups be on the same side as each other, or when you reduce it with lithium aluminum hydride, you would only get one product, not two. Either way, right, you would get the single alkene upon dehydration. Right, so all of these products, the other one, well, there is only one other one, right? Because that one's, if you flip the stereochemistry, you get the same product. All of these are going to eliminate to give you the same compound. Right, you're going to dehydrate that to generate this. But you're also going to dehydrate the other ones to generate the same thing. And they all dehydrate the sulfuric acid to get that product. This one will dehydrate to give that as a receiving mixture. This one would actually dehydrate to give a pure isomer. Just that one. And not the other one. But, right, the two enantiomers have the same physical properties, so you don't know that you make two products. Unless you measure a rotation. So that was a little tricky. 17.53 out of the book.
Have you guys already done page 7?
I don't remember. I don't think so. No, we did not do page 7. That's one of the ones we didn't do.
Would you mind going through 7? Or Max, if you have anything else, or Emma, go first, but I just need help with that one.
We went over problems. Yeah, we didn't go over 8 either. We went over page 9. That was the first thing we did. So as soon as you see that sodium cyanoborohydride, the NaBH3CN, that is a reductive amination. Methanol is the solvent, it's also the proton shuttle, and it says pH 2 to 3, which means that we have this as well. So our source of acid, this is an acid catalyzed reaction, is that. So we have to recognize it as a reductive amination, or you're getting a 0 for AT. This is exercise 2112 from within the chapter. So the first thing we're going to do is we're going to protonate something. Probably this, actually. But that's not really a productive pathway, protonating that, because once you've protonated that, you can't use it as a nucleophile. So it's happening, but we're going to ignore it as leading nowhere. And since it's reversible anyway, it doesn't matter. We have added solution. What we really want to do is protonate the aldehyde. Make that carbonyl carbon subject to attack by the nucleophile. And then we're going to do a intramolecular nucleophilic substitution, or a nucleophilic addition reaction rather, to form a 500 group.
Dr. Weaver,
Yeah.
what coordinated the methanol in the very beginning?
Whatever acid you put in there to reduce the pH to 2 to 3. Probably concentrated HCl. But as soon as you see pH 2 to 3, you know you're in an acidic medium, which means there's some acid in there. And whatever that acid is, it's going to protonate the solvent. So I got to keep track of my protons and or my carbons and make sure I get the 500 ring. So step 1 is protonation. Step 2 is nucleophilic attack. And now we're going to do 2 successive proton transfer reactions so we can make this into a leaving group. And methanol, which is the solvent, is also the proton shuttle. So hopefully I didn't screw up. So this is on the way to imine formation, or iminium ion formation in this case. Protonate the carbonyl group, nucleophilic attack from the amine, take a hydrogen off the nitrogen, put it on the oxygen. Now we're going to boot out water. To form an iminium salt. If the sodium cyanoborhydride were not here, the last step would be deprotonation, and you'd end up with an imine. But the sodium cyanoborhydride is there, and it intercepts the iminium. So by donating a hydrogen, generate the amine generated one of the 5-membered rings. I dropped the aldehyde. Aldehyde's still there. So it's the first 5 steps. Reductive amination has the same first 5 steps as does amine formation to make the iminium salt. But now instead of taking that hydrogen off with methanol to form the imine, we intercept the iminium salt by reducing it. And sodium cyanoborohydride is not a strong enough reducing agent to reduce the neutral aldehyde, but it is a strong enough reducing agent to neutralize the positively charged iminium salt. And now you just have to do it again on the other side. Protein aldehyde. We have the intramolecular nucleophilic effect. That's a 5-membered ring that I've drawn strangely. If you want that to be a little neater, you can redraw it like that. So now we need to do proton transfer steps to get the hydrogen off the nitrogen and onto the oxygen. Step 2, this is step 8. And steps 9 and 10 are the 2 proton transfers. Step 11 is the loss of water. Generate another iminium salt. And then sodium cyanoborohydride comes in again. Intercepts that. So those 2 reduction steps are not reversible. Everything else in this reaction is. Generate the final product, which is that bicyclic amine. So 2 successive reduction aminations, one with the primary amine, and then a second one with the secondary amine. In each case, 5 steps to an iminium salt, which then gets intercepted by the sodium cyanoborohydride to form the amine. So 12 steps. You could have divided that up into 2 separate 6-step reactions if you wanted to, but reductive amination is a 6-step mechanism. If you didn't recognize it as reductive amination, then you were pretty well done. Well, not necessarily, right? Because you could still form the imine with the amine and the aldehyde in the presence of in this case methanolic acid. Methanolic acid and aqueous acid are pretty much interchangeable. Does that do it for you? Chapter exercise 21-12, on whatever page that is. Yeah, it's actually one that they work out for you, exercise 21-12 on page 974. They don't show the whole mechanism. They skip steps. Anything else? I'm going to stop recording and save it.